Before moving on to subspace trails, let's talk about a new paper about invariant subspaces. So once we have done our research on weak keys of AES, after some time we realized the new paper titled New Representations of the AES Key Schedule by Laurent and Pernod. So we thought that by reading the abstract of their paper, we thought that they did the same thing what we have done. So we thought that they independently discovered similar results, but it turned out that our approach and their approach almost has nothing overlapping. So this was surprising to us. What they did was as follows. They used generic algorithm, which I mentioned, which introduced by Leander et al. So they use this generic algorithm for invariant subspaces, but instead of round function, they use one round of the key schedule. So this is where our research and theirs actually differ. So recall that in the beginning of this video series, I used the generic algorithm on a keyless round of AES. So they said that instead of doing that, let's feed the key schedule to this algorithm. So they wanted to find invariant subspaces of the key schedule. So once they did that, they realized that, and they showed that AES 128 key schedule can be split into 4 independent parallel computations operating on 32-bit chunks up to linear transformation. So they discovered a new representation of the AES key schedule, and this actually by using this new discovery, they looked at the previous best attacks on AES, and one of the best attacks on AES are impossible differential attacks, and they realized that, and in these attacks, you know that you have to perform key guess operations and so on to discover the correct key. By using this new representation of the AES key schedule, they realized that they can eliminate some of the keys by like an early abort technique. So they improved the previous best impossible differential attacks on AES 128 by reducing the time complexity of those attacks. So this is another way of using the generic algorithm. So it might be actually a good practice to see what happens to other key scheduled, other block ciphers key schedule algorithm. So let's move on to subspace trails and see what is the difference between invariant subspaces and subspace trails. So recall that on the left, we have the picture for the invariant subspaces. To find invariant subspaces, we iteratively compute the image of the current subspace and map the span of it backwards through the inverse function until the process stabilizes. So assume that this is there is an invariant subspace for this block cipher, this keyless round function f, and this is the invariant subspace. Of course, you don't know it, but if you somehow choose a subset or subspace of this invariant subspace, once you map it using the f function and back, after you've done it a few times, you will realize that you get the invariant subspace. So this is how the idea works. But for subspace trails, and this is pictured in the right, all cosets of the starting subspace gets mapped to a coset of the ending subspace. This implies that the derivative of the round function is in the ending subspace. So as you can see, we are dividing the whole space into subspaces, and these are mapped to, all of them are mapped to other subspaces. So by the way, I think these pictures were drawn by Friedrich Weimer, so it is a good time to thank him. So as you can see, in this scenario, we have a single invariant subspace, so we try to stay in that subspace, but in this case, we have cosets and they are all mapped to other cosets. So the space U becomes V here, and the coset AS becomes, for instance, BT here, but still they are mapped to it. So this is why in this scenario, invariant subspaces, we are focusing on the keyless round function. So this attack is almost always on weak keys. But subspace trails are not affected by the key schedule algorithm. because adding something to this space as an XOR would also stay in the, will go to some other space or something, but still it will be valid for all keys. So our idea was to combine both of them because we couldn't attack AES using invariant subspaces. So we thought that maybe we can combine invariant subspaces with subspace trails. So this way we obtain weak key subspace trails. So the definition is as follows. Let k weak be a set of weak keys and let small k be the element of this weak key space. And with k, we represent a j-round key by k to the power 0, k to the 1, and so on. And let ui's denote a set of s plus 1 subspaces with dimension ui is less than or equal to dimension ui plus 1. So as we are going to apply the round function, we will be obtaining other subspaces, but the dimension might increase. This is why we have this definition. For each key in this weak key subspace, U0 to US is a weak key subspace trail of length S if each I, starting from 1 to S, there exists a non-empty set AI in this, the complement of the UIs, for which the following property holds. So for every AI in this set AI, there exists an AI plus 1, such that UI XOR AI is the when the round function with a key is applied to this coset is mapped to is a subset or of another subspace. So this way you are trying to find a path. So this is actually the idea behind subspace trails, but here we are focusing on weak key so that we obtain weak key subspace trails. So let's see this definition in examples to understand it better. So we are going to look at the subspaces of AES, and we are going to define the following subspaces. Ci represents the column space, Di represents diagonal space, ID means inverse diagonal space, and Mi is the mixed space. So let's see how we define them. So for the diagonal space 0, so we somehow assume that this is the 0th diagonal. So you might have differences here. So this is the whole space. So we are considering every element here. And these are, the remaining bytes are fixed. So they're constant. So you might XOR it with an A. This A is actually also, if you define it as a 128-bit value, A would have zeros here and non-zero values on the diagonal. So if you apply the S-box to such a space, you will observe that you are still within the space because anything in the A would map into A and a constant value will go to a constant value, so they will be identical. After the shift row operation, our differences, non-zero values, actually would go to a column. So this is why D0 here becomes C0 column space. So with DIs, we were representing a diagonal. So this was D0. And as far as I remember, this one with this value will be D1. And this with this will be D2. And this single value with these 3 C's would be D3. This is, as far as I remember, how we define them. As the column space, this is column 0, column 1, column 2, and column 3. As you can see, we are trying to see how the subspaces are mapped. So we are having a subspace of diagonal space is mapped to column space after the shift row operation. And once you perform the mixed column operation, you are going to have a matrix multiplication with this. So it is going to stay like this. And once you add a key, you're just XORing these values with a fixed value. So the space still stays the same. So this is why we have we don't have weak keys for subspace trails, but for invariant space subspaces, we have weak keys. So let's continue in this way. Now the column 0 after the S box is still column 0. And after the shift row, as you can see, instead of the diagonal 0, we have the inverse of it. This is how we define actually inverse diagonal 0. And once you perform a matrix multiplication to these values, you have to stay in a space which is actually the matrix multiplication of an inverse diagonal space, which we represent with M0. So as you can see, we obtain a two-round subspace trail of AES. As you can see, once you start with the diagonal L, XORed with some constant, so you start the coset. If you perform one round of encryption to this space, you obtain a column space XORed with some value we don't know. But again, once you encrypted one more round, you obtain mixed column with C. So this is actually from the paper where they introduced the subspace trails. But now let's look at the weak key versions of this. If you assume K is a weak key, so if you take two values from our invariant subspace X and Y, and if you perform 4 rounds of encryption on this X with a weak key and 4 rounds of encryption on Y with a weak key, and at the end if you XOR them, the result will be actually the matrix multiplication with something in this form, where zeros means there are no differences. So since we are XORing these two, we are looking at the differences. So these bytes will not have any differences, and we will have question marks, which means that they can have non-zero differences with probability 2 to the minus 32. So this probability will be actually helpful to us because this probability is a lot better than for a random permutation. Because if you look at the random permutation which we represent with pi, or in the case of K, which is not a weak key, the probabilities will be something like 2 to the minus 64. For instance, if you don't choose the key as a weak key, you are looking after 4 rounds of encryption, you are looking on the bytes here, and you're saying that they shouldn't have any difference. So as you can see, we have 8 bytes here, and each byte is consist of 8 bits. So this means that 64 bits. So for a random permutation or a AES with a random key, you would observe such a situation with a probability approximately 2 to the minus 64. But once you choose the key as a weak key, this probability increases to 2 to the minus 32. And this is actually coming from our definitions of the invariant subspace, because recall that we say that 2 rounds of encryption maps a invariant subspace to invariant subspace. But once you perform further rounds of encryption, this occurs with this probability, because if you can see, we said that left part is identical to the right part, right? So if this one doesn't have any difference, then this one will not have any difference too. So instead of 8 bytes, now we are focusing actually on 4 bytes, because left part is identical to the right part. So this is why the probability increases to 2 to the minus 32 from 2 to the minus 64. So we look at the other distinguishers, other type of distinguishers. So from the paper from 2017, where Grassi, Rehberger, and if I'm not mistaken, Ransom, which I actually have the references at the end, introduce multiple of 8 property for 5 round AES. So ID is as follows: considers a set of 2 to the 32 times D chosen plaintext, where you can choose D from 1 to 3, active diagonals. So this is an example for a single active diagonal. The number of fixed pairs of ciphertext which are equal in these anti-diagonals, for example, in this way, is a multiple of 8 with probability 1, independent of the secret key, of the details of SPACs, and of mixed column matrix. So let me explain what this actually means. So for the sake of clarity, without loss of generality, let's assume that D equals to 1, so that we can get rid of these here. So you start with a set of 2 to the 32 plaintext, and you encrypt them for 5 rounds, but these plaintexts are in this form. So after 5 rounds, you have 2 to the 32 ciphertext. So you look at them and check how many of them collide in this anti-diagonal. Okay, so you would observe that the number of collisions has to be multiple of 8. So this is a very strange way of obtaining a distinguisher. So they say that if you choose this kind of plain text, regardless of which secret key you are using, after 5 rounds of encryption, your collisions on these antidiagonals has to be a multiple of 8. So this is important because so far nobody could find a 5-round distinguisher for AES. But with this method, they obtained a 5-round distinguisher for AES. So this was the first time we obtained such a long distinguisher. And now we can use our invariant subspace to extend this distinguisher on more rounds, but with the assumption that we are using weak key. So let's look at the 5-round weak key distinguisher. So in this case, we choose plain text from the invariant subspace. So left part is identical to the right part. So in this case, the number of different pairs of ciphertext CI and CJ, which are equal in this bytes, you can choose in different forms. So in this case, we have chosen the bytes 0 and 5, 6, 7, and so on. And so once you XOR the ciphertext, the output should be something in the form is a multiple of 128 with probability 1, independent of the details of the SBox and the mixed column matrix. So as you can see, if you go back, Grassi et al. Obtained a multiple of 8 property for the whole 5-round AES for any secret key. But once you reduce the secret key to a weak key, we obtained a multiple of 128 property. So we can extend it to 6 rounds, but this time, instead of multiple of 128, we obtain a multiple of 2 properties. So the idea is the same. You start with this many chosen plain text, but this time, if instead of 5 rounds, if you use 6 rounds, you obtain a multiple of 2 property. So this is somewhat unexpected. As you can see, the best subspace trail in the literature is on 5 rounds, and this works with every possible key you can choose, which was introduced in 2017 by Grassi et al. But we use our invariant subspaces to turn these subspace trails into weak key subspace trails. So we extended this 5-round to 6 rounds, but this time it works only on this many weak keys. But for AES 256, we even obtain a 9-round multiple of 2 property for 2 to the 32 weak keys. So as you can see, weak keys act in a weaker way, let's say, because the cipher becomes less secure when you accidentally use a weak key. As you can see, if you use a non-weak key, your cipher is resistant against subspace trails because the best they can find, the best subspace trail with probability 1 we can find is on 5 rounds. But once you use a weak key from this space, we can even get a 9-round distinguisher.